In section 3.5, we learn another technique called implicit differentiation. So this is a little bit different than the shortcut rules we've been learning so far, but once we understand this method, then we can use it to figure out a few more shortcut rules. So I've pasted some graphs from your textbook below here, and we're going to use this to understand the difference between implicit and explicit functions. So up to now, the functions that we've been working with have been explicit. That is, that we can solve for the output variable in terms of the input variable. So we can write our equation in the form y equals f of x. But there are some functions that we say are defined implicitly. So for example, x squared plus y squared equals 25, or x cubed plus y cubed equals 6xy. Sometimes you can solve those for y and get y as an explicit function of x, and other times you can't. So in these pictures, let's suppose we're dealing with x squared plus y squared equals 25, as it shows underneath the leftmost graph, which of course means we can label here points on the axes. Okay, so we know those coordinates. So this is a circle centered at the origin with radius 5. Now if we try to solve this for y, we can, for example, subtract x squared from both sides. We can take the square root of both sides, but what that's going to do is give us plus or minus the square root of 25 minus x squared. So in other words, the positive square root is in the middle graph here. F of x is the positive square root of 25 minus x squared. And the negative square root is in the third graph over, and they've called that g of x. That is negative the square root of 25 minus x squared. So the thing is that if we solve this x squared plus y squared equals 25 for y, we actually get two explicit functions of x and not just one. And you can see that the circle fails the vertical line test, so it is not a function of y explicitly in terms of x. Now, just to give you a sort of preview of what we're going to be doing, let's consider a function f of x that is x squared minus 2x all raised to the third power. Now, using the chain rule that we've learned, we can find the derivative f prime of x by bringing the power 3 down in front, by taking the function as is and raising it to one lower power, that would be to the second, and then multiplying by the derivative of what I call that base function. So that would be f prime of x. Now, another way that we can look at this is we can think of the given function as y cubed. And so y is the base function x squared minus 2x. Now if we want to take the derivative with respect to x of y cubed, basically what we're saying is y is a function of x. So we're going to bring our power 3 down. We're going to take y and raise it to one lower power. But because we're differentiating with respect to x, we have to then multiply by the derivative of the we have to multiply by the derivative of the y. Right? That is its own function of x. So that is using the chain rule. Let me just clean this up a little bit here. Sorry about that. Which in this case, because y is an implicit function, because y is an explicit function of x, we can, in fact, find its derivative, and the derivative of y, which is x squared minus 2x, is 2x minus 2. And if we just substitute back in then for the y, we get 3 times y, which is x squared minus 2x squared, times 2x minus 2. So the substitution of y has been put in at the end. So the bit I just went through on the right side of the page there, that's kind of what implicit differentiation is like. The only thing is that most of the time we don't have y solved as a function of x like we did here, that allows us to get the derivative completely in terms of x's. So, as it says, we don't have to solve an equation for y in terms of x in order to find the derivative, but we use this technique known as implicit differentiation. So what we're going to do is differentiate both sides with respect to x, and then we're going to solve the equation for y prime or dy dx. So we assume that y is a differentiable function of x, but it may not be solved explicitly for x.